Okay, so last time we essentially stopped at this point. We were looking at the definition of a linear operator restricted to a specific subspace. Okay, so let's look at what we've said. So let's quickly review a little bit. So we were saying that, so if T is a linear, oh shoot, I forgot. What were the acronyms? There were a bunch of people who were answering there. So there was, what were the letters? There was A somewhere. What was the name of the, do you remember who was A? ALS, okay. I thought there were 4 people, no? Who was A? Okay, who was A? Do we have A? Okay, good. Who was L? You're L. Okay, who was S? You're S. There was one more person, no? There was just 3? Okay. Does somebody want to volunteer for helping me keep track that you're following? If you're not following, or you feel that it's okay, show of hands for those who feel the class is going too fast. That you're not, it's going fast. What's your name? Oh man. So I'll call you U, okay? So AULS. Okay, so that you can sort of, because otherwise everyone learns at a different rate, right? That way I have some sense of how things are going. Call it. Okay, so right. So suppose T is a linear operator, right? It's going from V to V, and U is a subspace of V, which is invariant under T. Okay. So who remembers the definition of an invariant subspace? Do you remember the definition? Invariant subspace. Exactly. Okay. So the definition of invariant subspace was that if U belongs to, say, or let's say little v belongs to capital V, then TV has to belong to capital V, right? For all of it. So if this is the case, if V is such that for all V in capital V, TV belongs to capital V, then V is an invariant subspace. Is that okay? All right. Okay, so this was the definition of an invariant subspace. And what did we say about one-dimensional invariant subspaces? Was there some relation to eigenvalues? There was, right? Okay, so I'm just quickly reminding. Fantastic. Okay, so now what we're going to do is we're going to look at a linear operator, but we're going to restrict it to some subspace U of V. So if U is some subspace of V, we want to understand how T acts on U, okay, on this invariant subspace. What we're going to do is we're going to define 2 other operators. So using U, we will define this operator called T restricted to U. Okay. And we'll define T quotient of U. So this part we're going to skip. Okay. In the first part of this lecture, we are going to skip this. Today we won't look at this. Okay, we'll focus on just this part. And the definition is very simple. So let's suppose T is a linear operator on V and U is some subspace, then this restriction operator T restricted to U is defined as follows. So it's basically defined as T acting on U. Okay, no difference. The only difference is that we have restricted its domain. Okay, so remember T was defined on what? It was a linear operator on V, right? Now it is a linear operator on U. So T restricted to U is only restricting the domain. Okay, but we have to make sure that it makes sense. You cannot do it in general, right? So what property of U do we need for this to make sense? Okay, so let's recall. A linear operator does what? It maps, say it maps V to itself, right? In particular, right? So if I looked at some subspace U of V, okay, and I applied T on some vector from, say, U, right? In general, it did not have to belong to, so this was not required to necessarily belong to U, right? This was not guaranteed. This is not guaranteed, correct? Okay, so for this notion to make sense, you have to consider an invariant subspace of the linear operator. Otherwise, it doesn't make sense. Is that okay? All right.
Talk of direct sum, take off direct sum, but subspace that of direct sum. Can I say that for every invariant space, I should be able to form a direct sum and take those given?
let's come to those things afterwards. Let's yeah. If there's a so let me just say that this in general. If you have a question which is about clarifying what is happening in class, that is good. If you have a question that is beyond what is being covered a little bit, you can still ask. I might not be able to answer. Okay, but most of those things we should discuss separately. Okay, it's just so that people don't lose track in class. That's okay. All right. So is the definition clear? Is it making sense? A U L S should make it A U S L because I have to look. It's left to right. Okay, good. All right. And for the quotient operator, what we're going to do is okay. So this we'll cover later. Okay, this is we might. So for what happened here? Okay, I don't know what happened. Let me screenshot again just in case. Okay. Right. So for both operators defined above, let's take a moment to ensure that they're well defined and operators in their domain. So this I already told you, right? So the restriction of T to U makes sense because the domain of T is restricted, and you can think of it as a mapping into U instead of V, right? And the condition that U is invariant under T is crucial for this to make sense. This is what I just explained to you, right? Okay. So this is what allows us to think of TU as an operator. I'll just skip for now. And how is it all used? We'll actually see how it is used explicitly. So this discussion is also going to require this T given you. So we're going to skip this part as well. And all right, so let's look at an example. Suppose this is your operator. Okay, so the operator is defined as Txy is y comma 0. So you just look at the second component, make it the first component, the second component 0. So the example is asking us to do the following. It's saying show that U is invariant under T, and T restricted to U is the 0 operator. Okay, so let's see. The definition of U, sorry, I didn't tell you. The definition of U is just vectors where the first component is non-zero and the second component is 0. Okay, so let's look at such a subspace. So we want to check that this is invariant under T. So okay, so let's try to do that. So let's take a vector x comma 0 in U, right? And let's apply T to it. So what do we get? We get 0 comma 0. Right? Because it's just picking the second component, which is already 0. So this basically is just the same. It belongs to you, right? Because it's a 0 vector, and every subspace will have at least a 0 vector. Space has the 0 vector, right? We know this. This is fine. So therefore, what was the requirement? The requirement was that if you have little u from capital U and you have TU, then it should belong to capital U, which it does. It does so trivially, but it does. Right? What was the acronym? AULS, ALSU, AUSL, AUSL. Okay. So A is fine U. Is it okay? Is the definition SL? Okay, good. Ready. So this is fine. Now what we're going to do is, so that was the first part, right? So it said that this is indeed an invariant subspace. So this is fine with everyone, that this U is an invariant subspace of T. Okay. Second step is, there does not exist a subspace W on F2 that is invariant under T and is such that F2 is the same as U direct sum of W. Okay. So it's asking us to prove something interesting. I think there does not exist some other subspace such that when you direct sum it with the invariant subspace U, you get the entire space F2. Is the statement clear? A is the statement okay? U. Okay. So the statement is saying the following. So it's asking, does there exist? So does there exist, question mark, a subspace W such that F2, oh, so sorry, such that W is invariant under T, and U, oh sorry, W is F2 is U direct sum W. Is the statement okay? Okay, that's what the example is asking. Can you find such a subspace? All right, so let's do that. Okay, so how does the example look at it? It says, suppose W is a subspace of V. Okay, such that this condition holds. Right? It's just assuming the for contradiction, it's assuming what is supposed to be impossible. Then it says that the dimension of F2 is 2 and the dimension of U is 1, right? So dimension of W has to be 1. Okay, so this is just saying that dimension of, so if you have like U is direct sum over UI, then dimension of U will be sum over I dimension of UI. It is just using that part. Okay, if you've not seen this before, we'll add it in some I think in your seventh assignment, whichever assignment you have a bunch of questions about building intuition about direct sums. Okay, so the intuition is just that they're acting on you just the easiest way to think about direct sums is like in terms of matrices, if you like, they're like acting on different blocks essentially, intuitively. Okay, so the dimension you will add for this, and this. If you take the direct, is that okay? Intuitively, does that make sense? What was it? A, U, S, L. Okay. All right. So great. So this is basically it's trying to conclude what the dimension of W should be, right? So we know that F2 in this case. So this is yeah, okay, let me not right here. So dimension of F2 is 2, right? And we're trying to say this should be the same as dimension of U plus dimension of W, right? So this thing is 2, this thing is 1, and we can conclude that W is 1. That's all it's saying, right? So far so good. Yeah. No. Okay. Where did you get lost? Tell me. What was the last step that made sense? Which step? Which step? Was the beginning of B was okay? Yeah, I'm talking to you. Yeah, tell me. Everything is good? Oh shoot, I'm just getting confused with the head gestures. Okay, sorry. Good. All right. So now if W were invariant under T, then each non-zero vector in W would be an eigenvector of T. Right? Why? We covered this in the last lecture. So the statement is saying if W were invariant under T, then each non-zero vector in W would be an eigenvector of T. So okay, so W is a one-dimensional space, right? So W has essentially only one non-trivial vector, right? Everything is just scalar times that vector, right? So therefore, it's saying that if W were invariant under T, each non-zero vector in W would be an eigenvector of T. Right? That's the only way you can have a one-dimensional invariant subspace, right? This we already studied. Remember that a one-dimensional subspace is invariant if and only if you have an eigenvector. That the vector is. From last thing, no? Okay, so one-dimensional invariant subspace. You guys have to go back and take a little bit of a look, okay? Otherwise, if you're seeing it for the first time, you have to repeat a little bit. Otherwise, it will not make that much sense, right? So one-dimensional invariant subspace is equivalent to saying that the subspace, that single vector, so eigenvector. So each vector is eigenvector. Each vector in space in the subspace is an eigenvector. Right? LS. Wait, I think I'm losing people. A. Yeah. So this I'm assuming for now. Yeah. This you can assume for now. For this lecture, assume this. We'll look at the proof. I think it's probably in your assignment. If not, I'll add it. But we are assuming this, right? So the question was, there does not exist a subspace W which is both an invariant subspace, right? So there were these two, right? It was both an invariant subspace, and it was such that F2 is U plus W. So that is what we were trying to do. Is that okay? No? S? Sure? Is it okay? No. Tell me. Yeah, we're trying to prove the following, right? So we're trying to show that there does not exist a subspace W, okay, such that W is invariant under T, and F2 is U plus W. This is what we're trying to show. Okay, so to argue this, we are saying that, okay, let's assume that there existed such a W, and then we're trying to argue that, there would be some contradiction. Is that okay? Okay, I think this class I've lost everyone except for a handful of people. Is it making sense? No? It is? Okay. Okay. If something's not clear, please ask, okay? Because this is not much more than this I can do. If you need a minute, tell me if something's not clear. You have to ask. Okay. Huh. Yeah. So I'll go through the steps now. Okay. So this part is fine, right? So there whether or not there exists a W such that W is invariant. This is a okay. So now what we're going to do is we're going to look at this example. Sorry, we're going to look at the proof. The proof basically it does the following. So first it says we're going to deduce that the dimension of W is 1. This is the first thing. Okay. And this is just coming from this assumption that for direct sums, you can just sum the dimension. Okay? And then the second part is saying the following. It's saying that oh yeah, so we basically just stopped here, right? We didn't even complete the argument. Okay, so that was the first step, that this dimension has to be 1. And then we said because it's an invariant subspace and the dimension is 1, right? We know that every non-zero vector in W has to be an eigenvector, right? Because it's a dimension 1 subspace. So it's essentially just one vector scaled, right? That's all the characterization of the space is, and it has to be invariant, so it has to send that vector to itself, some multiple of itself, right? That's the entire space. Okay, so every vector is an eigenvector. Is that okay? All right. Now the claim is that all eigenvectors of T are already in U. Okay, this is an interesting claim. So what it is saying is that the eigenvectors of this linear operator T, they're all already in U. Why is that? Because 0 is the only eigenvector that T has. So what was T? T, remember, was doing what? It was sending x, y to y comma 0. Right? Correct? Okay. So what does that mean? X, y after the so this transformation gives you, yeah. So what is the definition of a eigenvector? It's lambda times v, right? TV is lambda times v. What is TV? TV here becomes y0, and lambda v would be xy. Right? So far with me. What was it? AULS A S L. Making sense? What's your name? Do you want to become S? Because S is almost always following, so maybe it's better. You want to become S for now? Okay. Yes. Is it making sense? Don't nod if it's not clear. Okay? That's like the most important rule. Do not nod if something is not clear. Sure? Okay. So now we have y0 equals lambda xy, right? Is that okay? And now what can you say? So you have y equals lambda x, and you have 0 equals lambda y, right? And lambda is non-zero, of course, because otherwise. Yeah. So you have y equals 0. Y equals 0 means x equal to 0, right? Do you see that? So the only eigenvector. So I just imposed this condition, right? For something to be an eigenvector, I imposed the condition. I got that v has to be 0. That is the only possible eigenvector of the operator T. Is that okay? Yeah. Okay. All right. So and 0 is already so all eigenvectors of T are already in U, right? Because oh no, I think I messed up a little bit. Yeah, no, what I said was wrong. Okay. What did I say wrong? I said 0 is the only eigenvector. I meant to say 0 is the only eigenvalue, because an eigenvector always has to be non-zero, right? What I said was wrong. Okay. So if x and y are non-zero, the only way you can satisfy this, right, is if lambda is 0. Correct? So you have so x and y. Yeah, so we have this equation, right? So we are saying what? So either so okay, let's see. So either y is 0, in which case this equation is fine, right? If this y is 0, then you would have 0 equals lambda x from the first equation. Correct? Okay, and if 0 equals lambda x, then If we set x equal to 0, then it's a 0 vector, which we don't want. So the only way you can satisfy this is when lambda is 0. Correct? Okay, so that's one option. The other option also you can check. So if y is not 0, then immediately you get lambda has to be 0 from this equation. Correct? So the only possible eigenvalue is lambda equal to 0. Correct? Okay. So that is the only eigenvalue. And all eigenvectors of T are in U already. Okay. So this one can check. So this the non-trivial eigenvectors. So your eigenvalue lambda is 0. Yeah, so okay, so your eigenvalue is 0. Okay, so now you've set lambda equal to 0, and this would give you y0 equals lambda x lambda y. Hmm. Mm. Okay, so 0 is obviously okay. So I think I'm messing up a little bit. Okay, so 0 is the only eigenvalue. This step is okay, right? And then it's claiming that all eigenvectors of T are in U. So eigenvectors of T, the most general thing one can do is you're sending it to y0, and it's lambda times xy. Okay. If the eigenvalue is 0, this would mean that what am I doing wrong here, you guys? Can you see? Can anyone see why all eigenvectors of T are in U? Louder? Yeah, so I was applying it in general, right? I was just applying, it's saying it for in general. It's saying all eigenvectors of T have to be in U. Hmm. Right. Okay, so I think I'm messing up some argument over here. Maybe I wrote it wrong from the textbook. Okay, but okay, 0 is the only eigenvalue. That is fine. This step, that all eigenvectors of T are in U, I am messing up the argument here. Okay, so
Lambda y has okay,
yeah, so I said either y is 0, right? Or y is not 0. Yeah, that is true. Yeah, okay. So from this, I think you get the characterization. You're right. You're right. Yeah, thank you. But what was your name again? Ashwin, yeah. So what Ashwin is saying is that, so I kind of got confused, and Ashwin is saying that, look, you already had the answer. The answer is right here. Right? So we said that when we impose this condition, let me say it a bit more clearly. So when we impose this condition, that y equals this condition, right? So then when we impose this condition, we get y equals lambda times x, or 0 equals lambda times y, right? Not or, and both of those conditions. Now, for this to be satisfied, they can be, so let's start with the second one right here. So this condition can be satisfied if either y is 0, right? Or y is non-zero, but lambda is 0, right? And we established that even in this case, you would eventually conclude that lambda is 0. Okay. All right. So this is fine. So we already know that lambda has to be 0. So we have y equals lambda times x, and 0 equals lambda times y. Okay. And okay. So now let's suppose y is non-zero. Okay. So if y is non-zero, then we have
then it becomes y is equal to
yeah. So we have 0. Okay. So we have something non-zero. So y is non-zero. Okay, and this has to be equal to lambda times x, but lambda is 0.
0.
Yeah, but that doesn't say anything. It doesn't say anything about x, right?
Says that y has to be y is 0 because it cannot be a eigenvector because there doesn't exist an eigenvector.
No, but here we're getting if y is not 0.
Lambda is 0.
No, y is non-zero. It's fine. We just have to show that x is 0. We have to show y is 0. Ah, that is true. Okay, yeah, that is true. Yeah, we have to show y is. Okay, so we got if y is non-zero, then lambda is 0. This is fine. And then we have,
Y has to be equal to 0.
but the equation is just this, right? xy equals
Y 0.
y is 0. Yeah.
If you prove that y is equal to 0,
Okay. If
then
y, wait. Wait. Hold on. Let's wait. So if y equals 0,
there is a vector that becomes x comma 0, right?
so x comma 0, yeah.
So this is the eigenvector. This belongs to you.
Yeah, that is fine.
And this eigenvector, since every eigenvector
No,
on x 0,
we have to prove that, right? That every eigenvector has to be of that form. What you're saying is, sure, if you take y equal to 0, you get an eigenvector. Tell me.
And if you're doing x from 19, I don't know, right? You say that number is equal to y comma 0 and then change it to 0.
Yeah, so this is equal to 0 comma. Yeah, exactly. Perfect. Yeah. So this lambda is 0, and then you get y is 0 is 0. Exactly. Okay, thank you. Perfect. Is that okay? So let me summarize the argument and where I got confused. What was your name again? Avni. Okay. So Avni and Ashwin. Yeah, thank you. So okay, so what I got confused about was the following. So we had to prove that all eigenvectors of T are in U. Okay. And how we did that? So first of all, the eigenvalue is 0. This was fine. This we agree on, that the eigenvalue of T is 0. This step was fine, right? So far we managed to make it. Now we try to argue that all eigenvectors of T are in U. How we show this is as follows. So we say that xy, when you apply T, would give you lambda times xy. Oh, sorry, y is 0. Oh shoot, I'm messing it up. It gives you lambda times xy, and this is equal to y 0. Is that okay? Is it making sense so far? I've not done anything. Everyone? Yeah? Okay. So now when you equate this, so we know that this lambda has to be 0, right? Exactly 0. So you have 0, 0. And what does that mean? Y has to be 0. Okay, so the only eigenvectors are of this form, x comma 0. Is that okay? Yeah? All right. So given that, what have we concluded? We have concluded that 0 is the only eigenvalue and all eigenvectors of T are in U. Is that okay? Okay. So what that eventually means is that wait, okay, so what is the final argument? So if W were an invariant under T, then each non-zero vector in W would be an eigenvector of T, right? And we've already characterized that there's only, like, all eigenvectors of T were already in U, right? So therefore W cannot be such a W cannot exist, because W would have to have an eigenvector, right? If it's an invariant subspace, it would have to be an eigenvector, and we already said that all eigenvectors are already in U. So you couldn't possibly not have an overlap with the vector space here. So W and U cannot have a common vector, right, other than 0. That's what it means, because you're writing a direct sum, right? So they cannot have a vector in common. And this argument is basically showing that all non-zero eigenvectors, all eigenvectors are essentially in U. There's no other eigenvector left. Is that okay? Yeah. Okay. Thank you, guys. Avni and Ashwin. Okay. Shall we move on? Is it okay? All right. So let's continue then. So for the third part, yeah, actually, let's see. So what is the third part? So the third part is about, yeah, it's about quotient thingy. So let's skip the quotient thing for now. Okay. So hopefully got some handle on. Sorry for the confusion. Okay, I kind of got a little bit lost with my own notation, but hopefully that was clear enough. Okay, so now let's continue. So now we're going to look at section 5b. So section 5b is basically going to look at eigenvectors and upper triangular matrices. Okay, so let's start with polynomials. So one of the main reasons that a rich theory exists for operators compared to ordinary linear operators is because uh, linear operators can be composed with themselves, right? So this we already saw in the previous lectures. So suppose T is a linear operator on V and M is some positive integer. We know that T to the M is just, you can define it as T being multiplied with itself M times. T to the 0 we can define as identity on the vector space. And if T is invertible, then T inverted M many times is going to give you T inverse to the M. All right. So T to the M times T to the N, we define as T to the M plus N. This is fine. Yeah. T to the Mn is T to the Mn. This is fine. This is like stuff you've already done. Okay, so we can be quite quick about it. Mn are arbitrary integers, T is invertible, and non-negative integers. For non-negative integers, we have T is not invertible. Is that okay? We can, sorry, what I meant was you can put non-negative integers in the power if T is, sorry, you restrict to non-negative integers if T is not invertible. Okay, you can put negative integers when T is invertible. That's basically what I meant. Is that okay? Wait, what was the acronym? AUSL, something like this. A U S S. Is it okay? No. Where did you get lost? Tell me. Last part meaning this the proof. Okay. Okay. Yeah. So the proof. Let me summarize one more time, just in case somebody also got left behind, because I made a mess today, right? So I have to be right. So I have to fix this. Right. So Ashwin and Avni basically suggested the following. So what we were trying to do was we were trying to show that there does not exist. So this is what we were trying to show. We're trying to show that there does not exist a W such that W is an invariant under T. This is what we were trying to show, right? So now F2. So that was one thing, and the other thing we wanted was that F2 is a direct sum of U and W, right? Yes. Yeah, that's what we were trying to show. Now the point is that we established already that so we assume that suppose it is the case that W is invariant under T. So the first thing we did was we established that the dimension of W is 1, okay, which basically means it's an eigenvector, right? Like it's basically it's an eigenvector. It's spanned by eigenvector of an eigenvector of T, correct? That's one thing. And the second thing we did was we showed with the help of Ashwin and Avni. I'm just saying the names because I'll forget. Okay. What did we learn? We learned that lambda is 0. That's the only possible eigenvalue of T by just doing some simple algebra. And then we showed that the only eigenvector is of this form, x0. Right? That's what we established. Now the point is that if these are the only possible eigenvectors and eigenvalue pairs, eigenvector pairs, right? Then it has to be the case, and they are already in U, right? And if you want to do a direct sum, it basically means that U intersection W is the 0 vector, right? It has to be the case. So what does that mean? It means that W could not possibly be, because you have to satisfy this condition, right? W have to be an eigenvector of T. But you cannot satisfy that because all eigenvectors are already in U, and U intersection W is pure. Is that okay? So this is why we conclude that such a W cannot exist. Make sense? Okay. All right. So yeah, for polynomials, you haven't missed much. For those of you who are still thinking about the proof. So for polynomials, we basically just have what we had earlier. So if you have a linear operator, T to the M is defined in a natural way. And if T is invertible, we write T inverse, and then we take powers, and the powers compose nicely. All of these things are fine. Okay, so AUSL. Are you guys with me? A? So far, USL? Sure? Okay. All right. So now let's look at the definition of a polynomial. So polynomial of T is the following. So suppose T belongs to a linear operator, and P is a polynomial given by the following. So Pz is this polynomial, which is fine. We have that for Z in F. Oh, sorry, for Z in F, right? So this is just the definition of a polynomial, right? Give me a second. I'll turn off this light. All right. So now, right. So what we're going to do now is we're going to look at the following. So we're going to look at so this is a polynomial, right? We can generalize it to linear operators, right? So instead of z, we can substitute it with the t, and we get the corresponding polynomial for linear operator. Yeah. Okay. All right. Okay. So this is a new use of the symbol p, right? Because so far we were using it for elements in the field, but now we're applying it to operators. So that's what it is. All right. Now, suppose D is a linear operator acting on polynomials. So this is an example, right? So suppose D is a linear operator acting on polynomials over the reals. And what is this linear operator? It's just a differentiation operator. So if you know differentiate, we've seen this many times. If P is this polynomial, P of the differentiation operator would basically be given by the following, right? So it would just be so here you have the identity operator. Here instead of x you put d, and here you put d squared. Right? There's nothing very complicated here. Is this okay? So it's just showing you how you would write a polynomial of an operator instead of nothing. All good? Okay. And now suppose yeah, and then how would it act? So if you apply it on Q, the first step is identity acting on Q, so you get Q. Right? The next one is D acting on Q, you get derivative of Q prime. Right? The last one is Q double prime. Yeah? No. Okay, okay. Yeah. So okay. So here what I said was the following. So I said, suppose this is the polynomial, right? So the polynomial is 7 minus 3x plus 5x squared. Okay. And P of D is the following. So P of D would be what? So we're just going to substitute x's with these, right? So 7 minus 3d plus 5d squared. This is fine. Okay. Now what we're saying is this thing is a linear operator, right? So we should be able to apply it on some vector, right? So let's apply to some polynomial. So what is the vector space on which PD acts? It's a linear operator on the set of polynomials. Okay. So let's apply PD on some x, or sorry, on some say Q is some polynomial. Okay. So Q is some polynomial, how will it act? Tell me, how will it act? Yeah, so okay, I can't fully hear you, but the idea here is that so this first thing is identity, right? So this operator is a linear operator, right? So when you act it on Q, you would get Q for the first one. For the second one, you'll get D acting on Q. Then you'll have 5D squared acting on Q, right? Exactly. And so DQ is just Q prime and D to Q is Q double. Is that okay? Good. What was it? AUS, ALS. Oh man, I can't even remember this. Actually, I should write it down somewhere. Right. So what is the acronym? ALS? AULS. AULS. AUSL actually. AUS. Okay. Good. Okay. A Q S. Yes. Yes. So it is exactly a linear operator. Yeah, so Q is in Q is in the okay, so what does PD act on? It's a linear operator on polynomials. So Q is just a polynomial. Is that okay? Perfect. Yeah, thank you for asking. Any other questions? There's just notation, right? Like it's nothing, it's just good to get familiar. That's it. There's nothing very complicated. Okay. So S L, okay, good. Okay. So fix an operator now. T, which acts on it's a linear operator on V. Then the function from PF to LV is given by P mapping to P of T. Okay, and this thing is linear, which is what you were asking. Okay, so they left it as an exercise, but it is the case. I'll be sure to include it in the section. You can just use the properties of linearity, of the fact that it's a linear operator, and we already proved that some of linear operators are also linear. But we proved that it's a space, right? We said that the set of all linear operators forms a space, so just essentially follows. Okay, so definition 5.19, product of polynomials. So now we are saying that if P and Q are polynomials, and you multiply PQ, then this polynomial is defined by P of that, like basically the polynomial P and the polynomial Q. It's just redundant definition. For they're just writing it for clarity because we are going to do it for operators as well. So any two polynomials of an operator commute as shown below. So what that means is that whether you do PQ of T or you do QP of T, okay, they're going to give you the same answer. And this is a little bit subtle because operators don't in general commute, but since everything is about T, it's going to be okay. It's not, if it's just like T prime and T, then things could get complicated because things don't commute. Okay, since it's just about T, things sort of are simple and they're going to get. All right. Okay. So let's maybe this proof I can leave this as an exercise. Okay, is the statement clear to everyone? Okay, so the statement is saying that suppose P and Q are polynomials in F, right? F is some field, T is a linear operator in V. Okay, so the statement is saying that PQ, so you consider the polynomial constructed with PQ acting on T. This is going to be the same as the polynomial on T and polynomial on Q on T. Okay? And P on T times Q on T would be Q on T and P on T. Is that right? Any questions? A, U, L, S, good. Okay. Okay. So the intuition is kind of very simple. It holds because when you're expanding a product of polynomials, right, you use the distributive property, and it doesn't matter whether you're using Z or T. Okay, because when you're expanding, you will get terms of so when, for example, when you write PQZ, you will get terms of this form. This is supposed to be Z. Of this form, J plus K, and it doesn't matter whether you do, you can split the J plus K, right? So that doesn't really affect so Tj plus K, you can write as Tj times Tk. That's basically what is underlying the entire proof. Is that okay? Okay, so I'll leave it as I'll give it to you as an assignment to quickly check. Okay, can we move on? Okay. Right. So now let's look at existence of eigenvalues. And so now we have like the first interesting statement so far. So the statement is the following. So it says, consider operators on complex vector spaces, and we'll show that such operators will have an eigenvalue. Okay, so the formal statement is that every operator on a finite dimensional non-zero complex vector space has an eigenvalue. Okay, is the statement clear? Because a priori, it's not clear, right, whether something would or would not have an eigenvalue. So if you have an operator, it's not at all obvious that there would exist some vector that you multiply with it and it would give you some scalar times that vector. It's not obvious. Right? So it's saying that for all operators on L of Cn, say for example, right? So finite dimensional complex space. So let's call this T. There exists W in Cn such that, I keep using the notation. So there exists W in this Cn such that T acting on W is lambda times W. Is the statement clear? A. Yeah, I think the dimension could be 0, right? Like you could have C to the 0. Like I think they're just being trying to be very strict that It could just be a field, right? A field is not it has no definition. Okay. Is the definition okay? Sorry, is the statement okay? All right. So let's see how to prove this. So suppose V is a complex vector space with dimension n strictly greater than 0, and suppose T is a linear operator. Okay. So now what we're going to do is we're going to choose little v in capital V with little v not equal to 0. Okay. So you choose any vector in the vector space, and we consider this set. So we start with V, we multiply it with T once, we multiply it with T twice, and so on. We multiply it with T n times. Okay, so we've considered a bunch of vectors, right? Now, these vectors are, so then these vectors cannot be linearly independent. Okay, why not? So what is the dimension of the space? N. And how many vectors are here? So can you have n plus 1 linearly independent vectors in an n-dimensional space? Okay, so therefore, these vectors, they have to be linearly dependent. Okay, all right. Now, what that means in particular, what does linear dependence mean? It means that there would have to exist some linear combination of these vectors that would give you 0. That's exactly the definition of a linear dependence, a bunch of vectors being linearly dependent. A, making sense? You? Yes, or just nodding like this? Sure. Okay. S? L? Okay. This is fine. Okay. So because V has dimension n and we have n plus 1 vectors, therefore they have to be linearly dependent, and if they're linearly dependent, they would have to exist such coefficients, and these coefficients are going to coefficients such that these vectors weighted by these coefficients give you 0. That is the statement over here. All right. So note that all of these cannot be 0. A1 to an cannot all be 0, right? Because otherwise the equation would become 0 is the same as a0v, and that in turn would force a0 to also be 0. Okay. So not only is it the case that all of these vectors cannot numbers cannot simultaneously be 0, we are saying that even these ones, a1 to n, cannot be 0. Because if they were 0, then that would force a0 to be 0, and that would mean everything is 0, which is not allowed. Is the statement okay? Yes? Okay, very good. All right. So now so we make the alphas the coefficients of a polynomial. Okay. So what we're going to do is consider the following polynomial. So we consider this, let's call it PZ. Okay. So PZ is defined as follows. It's A0, basically the same thing where you replaced TV with Z. Okay, so you replaced it with some scale. That's okay. All right. And note that by the fundamental theorem of algebra, this polynomial will have a factorization, right? Because it's just an n-degree polynomial, and then you can write it in terms of its roots, because you're in the complex plane, in the complex field. Okay, this doesn't hold in reals, right? Like in reals, you don't necessarily have factorization. In complex, you have factorization. Okay, so it's saying that you can write it as this product in terms of the factorization, where C is some non-zero complex number, of course. Lambda j is in the complex, and the equation holds for all z. Okay, and so here's an important part. So this little m is not necessarily equal to n, because a n may be 0. Right? So for instance, it's not clear from this expression that the degree of the polynomial is n, right? Because some of the coefficients might be 0. So for instance, an could be 0. So then you might not have as many roots. Is this okay? Yeah? All right. Okay. So now what we have the following. So we have 0 is this equation that we wrote, right? Because of linear dependence. Now here what we can do is we can pull out the v's into a separate vector and add identity. Okay. So from this step, so a to b is fine. A u L. Oh no, S L. Okay, good. That's okay, right? And then the next step, what are we doing? We are removing we are using the fact that the polynomial, these polynomials are the same, right? So now in the polynomial, we are substituting. So we can use this polynomial and substitute it. And it's a polynomial in T, right? Yeah. So this polynomial that we wrote, right? So this part you can write as P of T. So if I call this P, right? So this polynomial, if I call it P of Z, right? This expression here, you can essentially call P of T, right? And we essentially rewrote P of T. Yeah? No? You got lost? Okay. Right? So we just rewrote T and we rewrote it like this. Okay, so B2C is also fine. Make sense? Did you get lost? Tell me. All good? Okay. All right. And so then what does this mean? It means that, all right. So now we have that, this expression gives you 0. Okay. And what that means is that T minus lambda ij, T minus lambda ji is not injective for at least one j. Right? So what that means is that the kernel is non-zero for at least one of the j's. Yeah, because you have one of them has to be 0, right? So the kernel will be, so that entry will be in the kernel. So there has to be some vector that satisfies this. So you'll have at least one. Okay, and what does that mean in particular? In other words, that means T has an eigenvalue. Right? Because remember, to be an eigenvector, you have to find like some W had to satisfy this, right? And that's exactly what we concluded, that the kernel is non-zero. So there has to exist some W that would give you 0. Therefore, that means that there would be at least one of these lambdas would be an eigen. Is that okay? Okay, so congratulations, you proved like one of the really important results in the study of linear operators, that every complex operator in finite dimensions has an eigen. Yeah, okay. So this is saying that this means that T minus lambda j identity is not injective for at least one of the j's. So what does injective mean? So injective means that you're going one-to-one, right? Okay. So now what we are saying is that it has to be the case that at least yeah. So okay. So you have T minus lambda 1 by dot 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 T minus lambda m. So T minus lambda m. V is 0. So this we are guaranteed. Now, for this to happen, it has to be the case that wait, what did I do? So this is basically just saying that there is some vector, right, that is being mapped to 0 by, wait, what did I do? Shoot. Okay, give me a second. Let me see. Yeah, you guys can also think, okay, if somebody sees why it has to be injective, tell me and we can discuss. Yeah, so if it's not injective, but so sorry, what are you saying?
But I was thinking, of course, since it has to equal 0
Mhm.
and B is not equal to 0.
Yes, V is not a 0
B
vector.
is not equal to 0. And we know that the right hand side should be equal to 0. One of those terms, when B is up, one of those linear operators, the operators with B is upright, one of them has to be equal to 0. Only then we get the product of zeros. Product of that equal to 0.
Yeah, that part is not so clear, right? Because T minus lambda lambda identity, one of them,
When V is applied to one of it, it should equal to it.
yeah, but it's not V being applied, right? Like the operator's already acted on a bunch of these. But does that matter? Yeah, I guess you can commute them, right? I guess that's fine. Yeah.
Because they're all polynomials.
Yeah, I guess I think you can commute them and then it's okay. And then I guess one can conclude that at some point it has to be 0. Yeah. Yes, I think the argument is basically, I was a little bit concerned because I thought one cannot necessarily commute them, but I think it's okay because, so suppose for contradiction that none of these were, they were all injective, right? So if they're all injective, that means that none of the t minus lambda I identity, I think, yeah, maybe that's the easier way to think about it. Okay, so if suppose it's not, it is injective, right? So it's injective for all lambda I, then what that would mean is that none of these things would ever give you, will never be 0, basically, right? For V non-zero, otherwise you cannot invert it. If two things will map to 0, you cannot invert it. Or if two things map to 0, it's not injective. Only one thing can map to 0, right? Does that make sense? So injectivity implies that no non-zero vector can be mapped to 0. Yes, this would mean injective implies that no non-zero vector will be mapped to 0. Yeah. And if this were the case, then this equation can never be satisfied. Is that okay? That's all. Right. Sorry, I was just a little bit concerned that it might not commute, but that doesn't happen. Okay, so the statement was, okay, so the question was, how do we conclude this? Okay, so how is this true? How do you conclude that at least one of them has to be non-injective? Okay, and the answer is very simple. You just assume everything is injective. Okay, so what that means is that none of these operators will ever send any vector to 0. Right? They cannot. That's what injective means, because you're doing 1-to-1, and only the 0 vector can be mapped to the 0 vector. Everything else has to map to something else. Okay, and if this is 0, then at least one of them has to be. Yeah. So the input to the polynomial function. So when we went, yeah. So the input was z, right? So here the input was z, and now we said the input becomes t. Right? So it's exactly the same identity as it was here. We just use that. Is that okay? Any questions? Yeah. Because of the fundamental theorem of algebra. We're using another heavy theorem, but it's basically saying that with complex numbers you can solve essentially any polynomial approach. Right? Wait. Which step are you talking about? We use factorization only on this step, right? Yeah. So this is a property of complex numbers, right? Like this will not work for real numbers, for instance. If I give you some polynomials, it's not clear that it will have factorization in reals. So this is why the theorem only applies to complex numbers. So for complex numbers, we know that any polynomial you write can be factorized, and we're using that fact to deduce that at least one of these lambdas would be an eigenvalue. Okay. Is that fine? AULS? No, what is it? Yeah, U, L. V is a vector. Yeah. So here V is a vector. So the polynomial part was just this much. This is an operator, right? This is a linear operator, correct? V, this is a vector. This is a polynomial of T. Okay? Is it making sense? Any other questions? Okay. All right, so let's continue then. So now we have upper triangular matrices. Okay, so now in chapter 3, we discussed the matrix of a linear map from one vector space to another. Okay, yeah. So let's just directly talk about the definition. Okay, so the definition here is, so as before, we're trying to simplify things, right? Like, so we want to simplify the matrix as much as we can. We earlier talked about row echelon form and all these things. Now we're going to look at upper triangular matrices. The difference is that over there we were doing row operations, right? We were adding, subtracting rows and so on. Now we want to think about change of basis. We want to ask, is there a basis in which the matrix has a specific form? Okay, earlier we were allowed to add, subtract rows. Now we're not allowed to do that in general. Right? We are just saying, is there a basis in which you would have such a transformation? Okay. All right. So, okay. So suppose T is some linear operator. Okay. So now I'm defining what the matrix of a linear operator is. Okay. So this we have seen many times before. So the matrix of a linear operator is basically going to be given by this expression where what you do is you take the basis. So suppose V1 to Vk is the basis. You look at how T acts on Vk, and you write down the matrix entries A, say A Ik, Vn. Right? Remember this we saw last a long time ago. Not a long time ago, in like one of the previous lectures. Right? This is what was defined to be the matrix corresponding to the linear operator. Right? That you apply it on some basis and you look at the matrix corresponding to it and then you put this. Yeah. Okay, good. So now what we're going to do is we were using TB for exactly this in Hoffman and Kunze. Because this is the notation. I'm just trying to recall the connection that we had earlier. So B was B1 to Vn. Right? This was the ordered basis. Okay. Right. So the matrices of operators are square instead of being rectangular. So this we know. If T is an operator on Fn and no basis is specified, assume that the basis in question is the standard one. Just some standard convention. Nothing very complicated. Yeah. Okay, and one can think of the jth column of empty as T applied on the jth basis vector. Okay, this will be quite useful. Okay, this I already explained once. So if you have like some matrix A, B, C, D, E, F, G, H, I, right, and you apply it on 0, 1, 0, what this is going to do is it's going to pick out the corresponding column. Okay, so this is just something to keep in mind. So here's a small example. So suppose your linear operator was given by the following. So T acting on x, y, z, it was 2x plus y, 5y plus z, and 8z. Right? So suppose this is your linear operator, and you wanted to find out what the representation of T would be in terms of n. What you're going to do is you're going to basically write T in terms of the. So if you want to do it in the standard basis, for example, you will just do the following. So you will write T1, 0, 0. And then you will write what this looks like in terms of the, in terms of the matrix, and then you can essentially read off. So, because if you put x equal to 1 and all other 0, you will have 2, 0, 0. Right? And this, like I said, would give you the first column of the matrix. Right? This is what I was saying here. Right? Whichever basis element you put, it will give you that corresponding column. So if you put T1, 0, 0, it will give you the first column. So this is the first column. Is that okay? I'm just using this definition. Okay, there's nothing mysterious happening. I'm just using this definition. All right. And then similarly for T 0, 1, 0, what would be the answer? A. Yeah. So what is the second column? It's 1, 5, 0. Yeah. So I'm just putting y equals 1 here, and others are 0. Okay, so you get 1, 5, and you can check this sort of checks out. Is that fine? Matrix representation. Okay. All right. Okay. So now, okay, the central goal of linear algebra is to show that an operator T, that for a given operator T, there is a basis with respect to which T has a reasonably simple matrix. That is what we want to argue. And to make this vague formulation a bit more precise, we might try to choose a basis of V such that MT has many zeros. Okay, so in particular, they're going to try to look at a triangular matrix. Okay, so let's see. So if V is finite dimensional complex vector space, then we already know enough to show that there is a basis V with respect to which T has zeros everywhere in the first column except possibly the first entry. Right? So it would basically have this form. We just proved this, right? Like we just proved the theorem that there is an eigenvector. Right? So what is an eigenvector? So it's saying that T acting on V would give you some lambda times V. So at least for this vector V, when you write the decomposition, right? So suppose you make it into a basis, they call it V1 to say Vn, right? So T acting on V1 is what? Is lambda times V1 plus 0 V2 and so on, right? And these coefficients give you the column, right, of the first matrix. So that's what it is. Is this clear? Yeah, no? Looks like you guys got lost. Is it making sense? Tell me. Said that to you guys it makes sense. Yeah. Okay. All right. Okay, so this is already, so we already know this, and we're going to try to strengthen this result. So let lambda be an eigenvalue of T. Okay, and we know that this exists from the theorem we just proved. And we want to extend V to a basis of little v to a basis of capital T. Okay. Then the matrix of capital T with respect to this basis will have the form that we described above. This is just saying in words what I just explained to you. Okay. So what I explained here is basically what is being said here in this description. Okay. So it's just saying from the theorem that we just proved that there exists one eigenvector. Right? Because we said there exists one eigenvalue at least, so there exists one eigenvector at least. And if there is an eigenvector, you can always write, you can extend the basis. Suppose this was the eigenvector, you can extend the basis in some arbitrary way. And you know that when T acts on that eigenvector, you will get lambda times that eigenvector plus zeros everywhere else. Okay? And I just told you that when you write it in this decomposition, these coefficients give you the column of the corresponding matrix in that basis. No, you're getting lost. Okay. So let's look at it carefully one more time. So, okay. Yeah, so let's look at this representation. Maybe this is easier. So this matrix, right, that he's written down, he said that the entries of these matrix for a linear operator relative to some fixed places is given how? It's given by looking at how this linear operator acts on the basis elements, right, in terms of these coefficients. Okay? And you see this so for a fixed k, this gives you a column, right? So A1, K, A2, K, A3, K, A and K. Okay, so if you act T on some vector and you write it down as a linear combination of the other vectors, the coefficients will give you the corresponding column in the matrix representation. Is this okay? Okay. So now all I'm saying is that from our theorem, right, we just proved that there has to exist at least one eigenvector. Correct? When we have T acting on this eigenvector, okay, so suppose V is the eigenvector, and these other objects are you just extend to make a basis. Okay, so then T acting on V1 would be what? It would be lambda times V1 and plus zeros everywhere else, correct? So then what would the first column look like? Lambda and zeros, right? That's all it was saying. That this is what the form of the matrix. Is it clear? A? Yeah? Okay, yeah, so that's all the discussion was. There's nothing very deep happening. All right. Okay. So yeah, okay, we can skip this. This is not actually fully correct. Okay. So all right, so now we have a definition of a diagonal of a matrix. Okay, so this we are going to skip. We understand what a diagonal of a matrix is. Okay, it's just saying that if it's a big matrix, you basically look at the diagonal entries. This is what we mean by diagonal of a matrix. Is that okay? All right. Now we have a definition of an upper triangular matrix. It says a matrix is upper triangular if all the entries below the diagonal are zero. So in particular, it has this form. So you have lambdas, some eigenvalues, or sorry, some values. Okay, some non-zero entries potentially, and this block has to be zero. Okay, so you understand what upper triangular means, everyone? A U L S. Oh, sorry, S L. Okay, good. Okay, so upper triangular matrices can be considered reasonably simple. This is mumbo jumbo, that's not needed. The following proposition demonstrates a useful connection between upper triangular matrices and invariant subspaces. Okay, so what I'm now going to do is I'm going to assume that this proposition is true. Okay, and I will try to prove the main theorem that you want to prove, which is that every complex matrix can be written as an upper triangular matrix. Good, that is what we're going to prove. So it's important that you understand the statement of this proposition. We are going to use it. Okay, the proof I'll have to ask you to read later. Yeah. Uh-huh. Sorry, say it again. We don't have. Yeah, that is not the final form. Exactly. Yeah, it's not. It's not upper triangular. No. We're saying you choose whatever eigenvector you have, and it's one vector, right? Using that vector, you can make a basis, extend it to make a basis. So in that basis, it would have this form. Starting that, yeah, exactly. Okay, is that clear? The question was, the answer was clear to the question? Okay. All right, so let's continue then. We have, right, so proposition 5.26 is saying the following. So it's saying consider, so conditions for upper triangular matrix. So suppose T is a linear operator in V, V1 to Vn is a basis. Okay. Then the following conditions are equivalent. Okay. So it says the matrix of T with respect to V1 to Vn is upper triangular. Okay, so there is some basis relative to which the matrix has this form. Right. So this is 0 and then there's non-zero entries over that. The second one is this is the one that we're going to use a lot. Okay. So we're going to use that T of Vj. So if you look at the jth vector, it will be in the span of V1 to Vj. Okay. It's not hard. It's like relatively simple algebra, but I'm just telling you that this is the case. Okay. So T of V1 would be in span of V1. That's obvious. T of V2 would be in span of V2 and so on. V1, V2, and so on. Okay. Is the statement okay? Yeah. So it's equivalent. So if you can show this, that would imply that the matrix is upper triangular. If you have an upper triangular matrix, it would imply this is the case. That is what. All right. And the third one is saying what? It's saying that the span of lambda1 to lambda j is invariant under T. Because it's giving you invariant subspaces as well. So it's saying that span of V1 to Vj, okay, is invariant. So, span. So basically each one of these is invariant. Okay, so these three things are equivalent. The matrix is upper triangular. Each of the T's satisfy this property, and each of these spans are invariant. Or these three things are equivalent conditions. Is that okay? Yeah. Okay. So now let's try to see how So I'm going to skip the proof. I'll give it as an exercise because now we are going super slow in class. It was partly my fault because of the example, but yeah, we're going very slow. So let's try to at least prove the main theorems. Okay. So there are two proofs for this theorem. We are going to look at only one because the other one requires quotients. So the theorem statement is the following. Because the theorem statement is that suppose V is some finite dimensional complex vector space, and T is in this is a linear operator on this, then T has an upper triangular matrix with respect to some basis. Okay, so regardless of what operator I give you, as long as it's an operator on finite dimensional complex vectors, it's going to have a upper triangular matrix. That's okay. So let's see how the proof goes. So what we're going to do is we're going to do the proof by on the dimension of the vector space V. So we already know that when the dimension V is 1, it is upper triangular by definition. Right? Because it's just a 1 cross 1 matrix, it can have only one entry. So it's upper triangular. There's no lower half. Right? Okay. So now suppose that the dimension of V is strictly greater than 1. And the desired result holds for all complex spaces whose dimension is less than the dimension of V. Okay, is that clear? So we're saying that suppose So what you know induction, right? Everyone knows induction here, right? Yeah. So now what we're going to do is we're going to assume that this dimension, suppose the dimension is m or n. Okay, so suppose dimension of V is n. Then we're going to assume that for for n minus one dimensional spaces, the statement of the theorem is true. That for n minus one dimensions, everything can be made into a triangular triangle. Is that okay? Okay, so let's see. So let lambda be any eigenvalue of t. Then from theorem, and this we know from theorem 5 point or whatever, the theorem that we just proved, right? That there would exist one, at least one eigenvalue lambda of this linear operator. Let u be the range of t minus lambda I. Okay, so that's just the definition. It's the set of vectors you can get vector on t minus lambda I. So that's the set of vectors. Okay. Now, since t minus lambda I is not surjective, right? This we just argued, right? Because there is one vector that is being mapped to 0 because it's an eigenvector, right? So tv gives you lambda v. So that implies t minus lambda identity v is 0, right? So there is at least one vector that is also being mapped to 0 in addition to 0. So it's not surjective, right? It's not one-to-one. So therefore, it must be the case that dimension of u is smaller than dimension of v. So the range has to be smaller than the dimension of the space that you're in. Okay, this is using rank nullity, right? This you know very well. We studied. So if the kernel is non-zero, then the space is going to. Is that okay? Yeah. All right. Now the claim is that u is invariant under t. So this space, this range that we wrote down of t minus lambda I, this is invariant under the operation t. So how do we see this? It's not very hard. So suppose u is some vector in u, little u is a vector in capital U. Capital T times u is going to be t minus lambda I acting on u plus lambda u. So I just added, subtracted, right? The second, right? That's fine. Yeah. All right. And so therefore, clearly t minus lambda I acting on u would belong in u. That is just because u is the range of this operator anyway. Right? So that's how we defined u, right? U was defined to be the range of t minus lambda I. So any vector acting on t minus lambda I would give you u, would be a vector in u. This is fine. Okay. All right. And now lambda u already belongs to u because it's a vector in u, right? Okay, so the linear combination will also be in u. Okay, so this proves that u is an invariant subspace of t. Is that okay? Yeah. All right. So now we can talk about t being restricted to u as an operator. Right? This we can do because we established that if you have an invariant subspace of an operator, then you can restrict the operator to that invariant subspace. Right? Okay. So now by our induction hypothesis, we know that there is a basis u1 to um of this u. Right? So remember, u is now a smaller dimensional subspace. And for smaller dimensional subspaces, if we consider operators on those, we already assume by the induction hypothesis that they have an upper triangular form. Correct? Okay, so if there is some basis u1 to um for u, with respect to which tu has an upper triangular form. So this is just from the induction hypothesis. Okay? All right. So therefore, for each j, we have from the proposition that I said, let's take it on faith, okay, that tuj will, which is the same as t restricted on u acting on uj, is going to be in the span of u1 to uj. Right? Remember, this was the shoot. This thing is not connecting. So the statement was this, right? That t acting on ui was going to be in span of u1 to ui, right? This is what we said was equivalent, right? If you have an upper triangular matrix, then we said it's equivalent to checking that these conditions hold, right? So because it's upper triangular, we know that this is going to be true. With me so far? Yeah? No. Okay. All right. Now what we're going to do is we're going to extend this basis. So u1 to um, this was a basis for u. We're going to extend it to the basis of v. So v1 to vn, whatever. Right? So we've extended this. And for each k, it is the case that tvk can just be written like this. This is fine. Right? You just added, subtracted lambda times identity. Right? And now we have that the note is that T minus lambda I Vk belongs to U. Right? Because U, what was the definition of U? U was just the range of T minus lambda identity, right? That was just the definition. So any vector acting on T minus lambda will obviously be in the range. So that's not a surprise. Okay. And so what is the conclusion? The conclusion is that for each k, it holds that tvk is going to be in the span of u1 to um, right? Because this part, and in the span of v1 to vk, because this is the only other part that we had in the action of t acting on vk. Right? So there's a vector which is staying in u, and there's just this extra part which is coming from vk. It's not going to any other part in the vector space. Okay. And so what that basically means is that we're able to show this condition. And remember, what was this condition? This is exactly the condition that we wanted to show, right? So we wanted to show that T of Vk is going to be in the span of, all the vectors that we have until the kth vector. Okay. Okay, I'll review it again, okay, next class. But just try to make sure you're understanding the steps separately. We'll stitch it together one more time next class to review that everything something makes sense. Yeah. So the rough outline is that we said that we want to prove that every matrix has an upper triangular form. We said in the base case everything is okay. Now to look at the case with the general case with dimension n, we're going to assume that the n-1 dimension case works. The n-1 dimension case basically told us that you would have these vectors which are in in the restricted space which satisfy this property. Using that, we are able to show that the same property will also hold in the larger space. That is the high level idea. Okay? And the way we did it was basically by using this T minus lambda I, ensuring that these guys stay inside here. Okay. So yeah, go back, take a look. We'll review it one more time in the